In today's video, we're going to be talking about section 2.6. It's called a library of functions. And so far we've already talked about linear functions, right? And when we were talking about linear functions, we had our point slope, and we had our slope intercept format or form. Right, and so for two real numbers, m and b, so I'm going to give you a formal definition. So definition. I'll pick a different color. Let m and b be two real numbers. Then something that looks like f of x equals mx plus b is called a linear function. So that's linear function. Linear function. And that's important for us to know because before, right, we were writing it as y equals mx plus b. And that was what we called a linear equation. But now we're talking about a linear function. And remember, functions have a letter as their name, and they take an input variable to map onto an output variable. And so a couple special ones is if m equals 0, f of x equals b is called a constant function. In that case, b is our value, that is our output regardless of our input value. And then another one, if m equals 1 and b is equal to 0, f of x equals x, so whatever we put in is what we get out, is called the identity function. And so let's look at a couple examples. I'll switch color. Examples. Write a linear function f that has these values. After you do that, graph these linear functions. So for our first one, and I'll give it as a pair of points, our function at -1 is -5, and our function at 2 is 4. And the second one, our function at 1 is a fourth, and our function at 4 is 2. And so you might want to go ahead and pause there, and we'll look at these in turn. So for our first one, where we have f of -1 equals -5, and f of 2 equals 4, first let's go ahead and rewrite these as pairs of points. So when x is -1, our output, or y value, is -5. And when x is 2, our y value is 4. And so since we know that this is a linear equation, we can go ahead and find our slope. So slope is our change in y over our change in x. So we'll give these names. Let me pick a different color. So we have x1, y1, x2, y2. So here we have y2, 4 minus y1, -5, over x2, 2 minus -1. 4 plus 5 is 9, 2 plus 1 is 3. Our slope is 3. So now we have y equals 3x plus b, and we can pick either of our points. Let's go ahead, we'll use our second point since both of those are positive. So y is 4 equals 3 times 2 plus b. So 4 equals 6 plus b, and b equals negative 2. So if we put all of that together, we have our function of x is equal to m, our slope, x plus our b, which is negative 2. And so that's how we would write that linear function. And then it says, let's go ahead and graph it. And so I'm going to see if I can squeeze it in here on this window. So we know we have 2 points, negative 1, negative 5, so negative 1, 1, 2, 3, 4, 5, negative 1, negative 5, and 2, 4, 1, 2, 1, 2, 3, 4, 2, 4. We connect those. That's our x value, that's our y value. And so because m is positive, it increases from left to right, and we see that x-intercept of negative 2 right there. Good. I'll leave that next one there for you to do on your own, and then we'll move on. So what we're going to be doing in this lesson is really just going through and getting all of our functions out there. So we have our linear functions, we have our square root, and our cube root function. We have what are called piecewise functions. And then we have a whole bunch more that we'll call our library functions. And so we've already talked about linear, so now we'll go ahead and talk about our square root and cube root functions. And then we'll talk about what it means for a function to be defined piecewise. And then we're just going to end with a bunch of, we're going to call our basic graphs. And we're introducing all of them here because for each of these, like our reciprocal function or our root function or our square or cube function, we're going to spend an entire day on each of these in turn. So, a bit more about square root and cube root. So it says sketch the graph of f of x equals the square root of x. Now it's important that the first thing we always do is we talk about our domain and range when we have something that isn't just linear, right? Because we know for a linear function, our domain is all reals and our range is all reals. But whenever we're talking about something like a root function, we know the domain, well, it can't be any smaller than 0. That goes to positive infinity. And this basic one, our range, if we were to graph it, we would see a 0 to positive infinity. And so we can go ahead and make a table for x values and then our f of x values. We can do 0, 1, 2, 4, 9. Square root of 0 is 0. The square root of 1 is 1. The square root of 2 is the square root of 2. It's about 1.4. If you type that in your calculator. Square root of 4 is 2. And the square root of 9 is 3. So notice that our square root function always takes the positive root value. And so we can go ahead and sketch that graph. Let me pick a different color. So at 0, 0, and let me put my tick marks in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3. And that should account for all of them. We have 1, 1, 2, root 2, which is about 1.5. 4, 2, 3, 4 goes all the way up to 2. And then at 9, we're at 3. And so we have something that looks like that. And we can go ahead and look at our cube root function. cube root. So sketch the graph of f of x equals the cube root of x. Now, unlike our square root, which can only return the positive value, because there is no way you can multiply two numbers to get a negative, with our cube root, we could get a negative. So let me go ahead and convince you of that. So we have x and f of x. Suppose I take the point -1. -1 times itself 3 times is -1. And so that means if I would put this -1 here, the cube root of -1 is -1. Now the cube root of 0, what times itself 3 times gives us 0? Well, that's 0. And now here we have what times itself 3 times gives us -8. Well, the answer to that's -2, because -2 times -2 is +4, times -2 is -8. And so you'll see that I picked these numbers 0, 1, and 8 because they give me nice clean numbers, and so I'll go ahead and pick 1 and 8 on the other side. The cube root of 1 is 1, and the cube root of 8 is 2. And so we can go ahead and graph that. So here we have 0, 0, 1, 1, and at 8, 1, 2, 3, 4, 5, 6, 7, 8, we're up at 2. So we have that bit, which kind of looks like the square root, right? But then if we work left, -1, 2, 3, 4, 5, 6, 7, 8, we have -1, -1, and -8, -2. We also have this opposite side. And so, right, it kind of looks like our square root and then rotate it around to the other side. It's a little less steep than our square root, because if I were to draw my square root on here, it would be similar in terms of this. But at 1, we're up at 1.5. And all the way out at 8, 9, we're at 2. And so, right, so we're a little less steep when we're looking at the square root. So that one here is the square root. So those are our ways to think about the square root in terms of a function. So now I said we were going to talk about something like piecewise functions. So a definition. In a piecewise function, different rules for assigning output values are used for different parts of the domain. You're like, what? Right, so whenever we were looking at, say, a linear or a square root, what we end up looking at is, oh, hey, no matter where we are in the domain, we plug it into that rule and we get an output value. But here we would have something, and typically by convention we'll use a capital letter to denote a piecewise. So capital for piecewise. We would say something like this. My function of x is equal to x squared whenever x is less than 1, and it's equal to 2x plus 1 whenever x is greater than or equal to 1. And so let's go ahead and work with that. So I'll rewrite that real quick. F of x is x squared whenever x is less than 1, and it's 2x plus 1 whenever x is bigger than or equal to 1. And I want to find f at 0, f at 2, and then sketch f of x. And so if f at 0, well, is 0 less than 1 or bigger than or equal to 1? Well, it's less than 1. So f at 0 is just going to be 0 squared, which is 0. Conversely, f at 2, because 2 is bigger than 1, we get 2 times 2 plus 1. And so here we get 2 times 2 is 4, plus 1, or 5. So f at 0 is 0, and f at 2 is 5. And we're going to want maybe just a couple more points, so I'm going to go to another slide and rewrite my point function. F of x equals x squared. Whenever x is less than 1, it's 2x plus 1, or x is greater than or equal to 1. Go ahead and make a table, not 0. That is our x. This is our big F of x. So 0, 1, 2, 3, and then 0, negative 1, negative 2. So big F at 0 is 0. At 1, it's 2 times 1, or 2 plus 1 is 3. At 2, 2 times 2 is 4, plus 1 is 5. 3, 2 times 3 is 6, plus 1 is 7. At negative 1, we have negative 1 squared, which is 1, so that's negative 1 squared. And here we have negative 2 squared, which is 4. And so to graph this, since 1 is our point of interest, I'll use a color here. At 0, it's 0. At 1, it's 3. At 2, it's 5. And at 3, it's 7. So that part is linear, because that's a linear equation. Now x squared, whenever we're less than 1, we have 0. Negative 1 is at 1. Negative 2, we're at 4. And if you remember, our x squared equation looks like this. And so maybe you didn't remember that. If you want to, well, we know that x squared of a half is a quarter. 0.75, a little bit higher. 0.99 squared, a little bit higher. All the way up till we get x equals 1. And so what we end up seeing, let me pick a different color for this, is on this side, it looks like x squared. And on this side, it looks like 2x plus 1. And so piecewise just means we're going to have 2 or more pieces of our function that are defined by a different rule. So here, let's look at another example. So sketch h of x, and big H of x is equal to the absolute value of x for x less than 2, and it's equal to x squared for x greater than or equal to 2. Put our commas in there just so you know where it splits. We'll go ahead and draw in our coordinate plane. We already know that 2 is going to be a point of interest, so 1, 2, 3, 4. We'll go just a couple this way. So at 0, we're at less than 2. So let me pick a color. And how about this? I'm going to use green for this one. And then I'll use another color for x squared. So when we're less than 2, so at 1, we take the absolute value. At 0, negative 1, negative 2. And so our absolute value is kind of this V shape. And normally it would continue to the right, and we can go all the way over to 2. But we have to stop there. And then we need to look at what it wants us to do with our other color. So whenever x is bigger than or equal to 2, so at 2, it's 2 squared. So at 2, it's 2 squared is 4. And then the next one, we have 3 squared is 9, and so I'm already running out of space. But from here, it looks like that. So again, reinforcing this notion of left of this point of interest, we have the absolute value of x, and to the right, we have x squared. And so that's one way that we can handle piecewise functions, is if we're given the function and we graph it. But then we can also be given a graph and it says, all right, well, give me the piecewise function. So give me just a second to draw this. So this is the point -3, 0. This is the point -2, 2. This is the point -2, 4. This is the point 2, 4, 2, 1, and 3, 0. And so go ahead and pause here and go ahead and try these and see how it works. See if you can make sense of what's happening. So we have a linear function on the left, we have a constant function up top, and a linear function on the right. And so what we can do is we can find the equations of the pieces. And so let me pick a different color. So our steps are 1. Find equation of the pieces. And actually, before we find the equation of the pieces, find the pieces. So let's say that this function here is big G of x, and that's for all three of these pieces. Well, big G of x then has 3 different pieces. It has a piece when x is less than -2. We have it whenever x is between -2 and +2. Oh, I need to write an x in there. And then we have a piece for when x is bigger than or equal to 2. Right? And that I found by looking at this point and that point. And so those are our 3 pieces of our function. And so we have a linear equation here, which as it increases left to right, so we know our m is going to be positive. Over here we know m is going to be negative. And here we know our slope is 0, so we have a constant. So it doesn't matter what our x value is, y is 4. So g of x equals 4 whenever we're between -2 and 2. And I want to take a moment to emphasize, notice that I put the less than or equal to here, but I didn't have an equal to there. And that's because whenever we have a solid dot, that means it's included, but when we have an open dot, it isn't. Just like this previous one, we don't have a less than or equal to, because it's an open dot on this piece, and then it changes rule once we get to -2. And so at this point here we have -2, 2, so we can look at our rise over run method. We go down 2 to get to 0, and left 1 to get to -3. So our rise is -2 over 1. -2 over -1, which is 2. So we have 2x plus, and now we need our intercept, and I don't have a lovely trick for this one. So what we'll do is we'll write, and I'm running out of space, y equals 2x plus b, y equals 2x plus b. Pick a point. We'll use that -3, 0 point because that looks like it'll be easy to work with. 0 equals negative 6 plus b, so b equals 6. So 2x plus 6. And then we have our piece on the right. Let me pick a color I haven't used already. So we can use our same slope. Our rise now is from 2, 1, we go down 1 over 1. So our slope is negative 1, negative x plus, and we need a b. So we have y equals negative x plus b. We'll again use this point because there's a 0. 0 equals negative 3 plus b. So b is 3, so y is negative x plus 3. And that's how we would write our piecewise function for that graph. We have we have g of x equals 2x plus 6 when x is less than negative 2. That g of x is equal to 4 when negative 2 is less than or equal to x is less than 2. And we have negative x plus 3 when x is greater than or equal to 2. Okay. So now what I'm going to give you is just the library of functions. And lots of these we've seen when we were talking about equations, but I just want to be able to give you all of these. So there are 12 of them. So let me see if I can manage to divide this in a way that might actually work. And I'll go ahead and put my coordinate plane in each one. And so when we're looking at our coordinate plane, here if we have something that's just constant at some point, that's our f of x equals c, our constant function. If we have something that passes through the origin with a slope of 1, f of x equal to x, remember we called that the identity function. We have something that can look like f of x equals x squared. The graph looks something like this u, and that's called our squaring function. If we have something that looks like f of x equals x cubed, this is our cubing function. And it looks like an x squared on this side and an upside down x squared on this side, right? Because negative 1 times itself 3 times is negative 1. If we have something that looks like f of x equals absolute value of x, it's called our absolute value function. It looks like a linear line on both sides. And in fact, our absolute value function can be defined piecewise as x when x is positive and the opposite of x when x is negative or 0. Right, because this piece is f of x equals negative x, and this piece is f of x equals x. And again, we're going to spend a lot more time with each of these, so there's no need to be like, well, how did you get that? Well, because we know we can plot them by plugging in points, but as we work with these, we're going to get more comfortable with them. So if we have something that looks like f of x equals the square root of x, or x to the 1/2 is equivalent, we know it looks like that, and that's our square root function. We also then have our cube root, which we talked about once already today. And that was f of x equals cube root of x, or equivalently, x to the 1/3. Now one that's new is our reciprocal. That's when f of x is 1 over x. And when we do that, we end up with two pieces that look roughly like this. Note that our domain is not defined for 0, so x can't be 0, so this graph has no value at 0. And no matter how big you get, positive or negative, will never hit that x-axis. And so it's kind of these two half circles. And if you want a nice picture of all of these, they're all in this section of our textbook 2.6. And so you can use them there. You can practice graphing them with a graphing calculator. And then we also have reciprocal square. So that's where f of x equals 1 over x squared. And now remember when we took like the absolute value, when it became positive, it was like a linear and then it flipped up. Well, because whenever we square something, it's always positive. Our reciprocal square ends up looking like the reciprocal function, but both sides are above the axis. Because -1 now, instead of going to 1 over -1, which was -1, 1 over -1 squared takes us to 1, right? And so it's like our reciprocal function, but all of it is positive. And we have just a couple more to look. I know this is a lot. But I just want to get all of these on your radar because over the next few weeks, we're going to unpack each of these in more detail. If we have something that looks like, we'll just call these generally rational power. And so this is where we're going to have something like f of x equals x to the 3 halves. I'm going to be drawing it over here. I don't know why I wrote it so far to the side. Well, that's the same as the square root and cubed. So we take the square root and we cube it, and we end up with something like that. If we have something over here, f of x, x to the 2/3, we end up having the cube root squared. So our cubed root function, remember from before, looks like this swoop to the right and then swoop to the left. But if we're squaring it, we're still going to have this to the right, but now to the left we're positive. And then we have one more, and I'm actually going to go to the next page for this. This is called the greatest integer function. This is f of x equals, and now our book uses this notation, where you have this like double bracket, but I would say more common, you're going to see it looking like this, and that's called the floor function, because you only draw the floor of our brackets. And what that means is whenever we graph our function, we always take the greatest integer less than our value. So 0 is an integer, and if I'm at a half, my greatest integer less than that is a half. And then I get over here to 1, but now 1 is an integer. 1 1/2 we round down to 1. 1 3/4 we round down, and then once at 2, we move up to the next integer. 2 1/2 round downs, 2 3/4, but then at 3 we jump up again, and it looks like this. And now as soon as we go left of 0 at -1/2, we have to round down to -1. At -1, we're still at -1. -1.5, we round down to -2. So we get something like this. And so you might also see this called the stair-step function, because it looks like stair steps. But the important thing to know is, if you want to remember this, this is the round down function. Because whenever we're at 1.5x, we round down it to 1. Whenever we're at 2.5, we round down to 2. Whenever we're at negative 1.5, we round down to negative 2. And so on, and so on. So I know that was a lot of graphs. It was a lot of graphs. But there are just a couple things that I want you to take away from this. So we've talked a little bit about linear functions. That's where we have f of x equals mx plus b. We looked at our square root and cube root functions. So we have our cube root and square root functions. So that's where we have f of x equals the cube root of x, or f of x equals the square root of x. And the important thing to remember that's different about these, the domain of our square root is just 0 to infinity, but the domain of this one is negative infinity to infinity. Piecewise functions are defined in pieces, hence their name. So we have piecewise functions. And I just want you to start getting familiar with how you graph a piecewise function, or given a graph, how you write the equation for a piecewise function. And then the next thing that's important is whenever we start working with more and more graphs, because really precalculus is the study of functions and their graphs, I want you to start to be familiar with our library of functions. Our constant function, I don't want to do this without making this completely messy. Our identity function, our squaring, our cubing, absolute value, our root functions, our reciprocal functions, our rational power functions, and then really the newest one here is our floor function. The book calls it greatest integer, so I want you to know that term, just like I want you to know their notation, but I will often write it this way. And so just as we start to work through this, we're going to get familiar with this library of functions, and the reason we do that is because once we're comfortable with those, we'll be able to begin graphing without finding each of the points. So next time, we're going to talk about transformations of functions. So we don't need to find the points. Don't need points to graph. And it's not transformations of just any functions, but transformation of library functions. All right. Have a great day, everyone.